So, welcome back to our video lectures on projective geometry. In our last lectures, we learned that there are important differences and commonalities between different Cayley Klein geometries. And this time we really want to focus on one specific Cayley Klein geometry that I repeatedly called hyperbolic geometry. There will be 3 videos about the topic of hyperbolic geometry, and these 3 video lectures will conclude our cycle of lectures on projective geometry. The reason why I'm specifically emphasizing this special kind of geometry is threefold. First of all, it's mathematically very beautiful. Second, it's really of historical relevance if you consider the history of mathematics as an important part of human culture. And as a third point, it's really a human story. So there are really, I would say, tragedies and gossip and all exciting things around this theory. So this lecture today will also be a little bit a historic viewpoint that gives somehow an idea of why these concepts are relevant. So let me first collect what we know so far and specify what we are talking about. So what we want to talk about is a Cayley Klein geometry, which is defined by a fundamental conic that in that case is real and non-degenerate. And we want to focus to the specific situation that we only consider the part inside the fundamental conic, where inside is again defined at those points from which you cannot draw real tangents to the conic. So if you are at the outside, you can draw real tangents, but if you are at the inside, you cannot. And it's for several reasons very interesting to focus on the inside here. So what do we know? So in that geometry here, we had some lines and we had points, and since I said I only want to focus on the inside of this conic, I'm only considering the part of the line that really lies inside this conic. And so we know that we have an hyperbolic length measurement. So if we go in unit steps toward the boundary, we will never reach it. We know that we have an elliptic angle measurement. Say if we have 2 lines here and we want to measure the angle, we can apply the formulas of Cayley Klein geometry, and since the 2 tangents at the point of intersection here will be complex, we get an elliptic angle measurement. And we also already studied the transformation group here, and it turned out that it is isomorphic to the transformations of a real projective line. And one of the reasons for that is that we can consider the fundamental conic as an isomorphic image of the real projective line. What we also already learned that most triangle theorems hold, at least sort of, with the twists that you have to apply to that. We already have seen there are such beasts like right-angled pentagons, and there are no rectangles. And one important thing, and this is the point why it makes sense to focus on the inside of that. If you consider yourself as a being living in the inside of that space, and you do this walking in unit steps, there is no way for you to escape. You are really trapped in the inside of this fundamental conic because with every finite number of steps it will not be possible for you to really reach the boundary. It may look like, if you look at it from our outside point of view, you approach it closer and closer. But if you have a kind of inside point of view, all these steps will look exactly the same, and you are literally trapped in that world. So it feels like an infinite universe, like our normal plane. So if we have an infinitely extending plane where you can also walk in any direction without ever reaching infinity, this here at the inside feels exactly the same essentially. There are some interesting things. So for instance, if you have a point, there are many lines through that, and if you have this point here which is not on that line, you see there are more than one of those lines, and we will see that this point will become extremely important when we look at it from an historic perspective. So let's take the historic perspective here, and taking the historic perspective means to start really, really early. We have to start with Euclid, and we are in the years somehow 325 to 270 BC, so we are more than 2000 years ago, and at that time Euclid did something extremely important for mathematics. He wrote what today is called the Elements of Euclid. This is a collection of altogether, I think it's 13 books, where he states the fundaments of geometry, of that what we today call Euclidean geometry. Euclidean referring to that person who most surely didn't look like that. So at that time there were no photographs, so this is a kind of artistic rendering of that really important person. So what it did in his Elements was something that changed mathematics in a really drastic way, because he was studying the inner workings of geometric objects, and for that he said, okay, let's do it in a logical and deductive way. And he perhaps was the first person who took that approach to mathematics by first formulating what he called postulates or axioms that describe what are the fundamental properties of our objects, and then derive conclusions from these postulates. So it's a kind of axiomatic approach to mathematics, and perhaps the first blueprint of an axiomatic approach. From a modern perspective, one could say there were several flaws in his thoughts, but all of them are minor compared to the giant step that he made by introducing this method, and all of them can essentially be fixed. So he posed 5 postulates. The first of them is a straight line segment can be drawn joining any 2 points. So I give you 2 points and you are able to draw a straight segment between them. The second postulate is the following: any straight line segment can be extended indefinitely in a straight line. So if you have those 2 points, you can, well, essentially walk in both directions and never reach an end of that line. Third postulate: given any straight line segment, a circle can be drawn having the segment as radius and one of the endpoints as center. So I give you a point and another point that define a segment. There is such thing like a curve of all points that have the same distance from the center through the other point, and this can be then for any points. The next postulate is all right angles are congruent, which means that if you have 2 lines like these 2 here, and you have a right angle between those 2 lines, and you have other two lines and a right angle between them. There's a kind of motion moving one to the other, so you can apply constructions you did here as well. Here it needs a little bit refinement to have that in precise terms, but it's okay if you understand what he means. And then comes the fifth postulate. And before I show you the fifth postulate, I want to remark one thing. These statements here are all pretty short. And now look at the fifth postulate. If two lines are drawn which intersect a third in such a way that the sum of the inner angles on one side is less than two right angles, then the two lines must intersect each other on that side if extended far enough. Got that? Actually, it reads somehow like the small print in a mobile phone license agreement, if you compare it to the other statements. And I won't explain what this exactly means, but I will give you some equivalent formulations of that in a minute. But what really happened is this last postulate here looks so different from the other four, and as a matter of fact, in his first 4 books of the elements, he only used the first 4 axioms and not the fifth. So he somehow seems to be very hesitant to use the fifth axiom, and people at some point started to question themselves, perhaps this axiom is superfluous. So perhaps you can get exactly the same geometry if you don't have this axiom, and perhaps it's not an axiom but a theorem that follows from the first 4 postulates. And well, let me first give you a few redefinitions of that, and here I call it the parallel postulate because it's best expressed in terms of parallels. I give you, well, a whole bunch of equivalent formulations. The most prominent one of them is perhaps the first one. There's at most one line that can be drawn parallel to another given one through an external point. So that means if I give you a line and an external point, there is at most one line that doesn't intersect the green line and passes through the external point, and in fact it turns out that if there is at most one, there is actually exactly one. So as a consequence of Euclid's axioms, this is equivalent also to saying that there is exactly one such parallel. This is called the parallel postulate. So for any line and any point not at this line, there's exactly one line that doesn't meet the other one. Here are another couple of equivalent formulations, and I want to read at least a few of them. The sum of the angles in every triangle is 180 degrees. There exists a triangle whose angle add up to 180 degrees. So you see, the angle sum of triangles are somehow very important in that context. The sum of the angles is the same for every triangle. There exists a pair of similar but not congruent triangles. If 3 angles of a quadrilateral are right angled, then the 4th angle is also a right angle. Oh, now some bells should ring in your head. This means rectangles exist. And we saw in hyperbolic geometry, rectangles don't exist. There exists a quadrilateral in which all angles are right angles. This is a rectangle. 2 lines that are parallel to the same line are also parallel to each other. In a right-angled triangle, the square of the hypotenuse equals the sum of the squares of the other 2 sides. Pythagoras. So Pythagoras' theorem is equivalent to the 5th postulate. There is no upper limit for the area of a triangle. So you see, if you take the first 4 axioms and consider them to be true, then if you prove that any one of those things here is a theorem, then you proved that Euclid's fifth postulate is actually a theorem. And if you prove that there are geometries in which the first axioms hold, the first four, but one of those things here becomes false, then automatically all of them will become false, and you will have shown that the fifth postulate is actually a necessary one. And somehow, well, this is what's happening in hyperbolic geometry. Let's look at the four axioms. So a straight line segment can be drawn joining any 2 points. And now let's again focus on the interior of a real non-degenerate fundamental object. I give you 2 points. And well, the segment between these 2 points is the segment we are asking for. Any straight line segment can be extended indefinitely in a straight line. This was essentially our walking in unit steps here. So walking in unit steps and never reaching the end is this indefinitely extending the line. So if you are a being in that universe, it really would feel as if you can indefinitely continue on that line without ever reaching an end. So how about the third postulate? Given any straight line segment, a circle can be drawn having the center as radius and one endpoint as center. I already talked about circles in Cayley Klein geometries, and it turns out this is simply true in this kind of theory. So if you have 2 points which correspond to line segments here, there is such a thing like a locus of all points of same distance to the center as your other boundary point. All right angles are congruent, so this essentially means I again can transform, say, one situation of a right angle to another situation of a right angle, and it turns out that this can be done by transformations in Cayley Klein geometry. So you can move one right angle to another one in Cayley Klein geometries. So and now comes the interesting point, fifth postulate. And I take the version of the parallel postulate. There is at most one line that can be drawn parallel to another given one through an external point. So let's take this line and let's take an external point. And you see in my world there are many. And actually it's almost trivial that there are many because, well, they are simply cut by our fundamental object. So they would intersect here, but they intersect outside of our world. So this geometry here really violates the parallel postulate. And the surprising thing here is not that this Cayley Klein geometry here violates the fifth postulate. The surprising thing really is that it satisfies the first four, because it's really tricky to get a system different from Euclidean geometry such that the first four things hold. And so essentially having this kind of Cayley Klein geometry shows that the fifth postulate of Euclid is indeed independent of the other four axioms. And if you look at the history, what happened, it's a really exciting history. Here what you see is my personal hall of fame of peoples that play an important role after things got to the point where people knew what is really going on. So the first three here, Carl Friedrich Gauss, János Bolyai and Nikolai Ivanovich Lobachevsky, can be considered as independent discoverers of non-Euclidean geometry. And these guys here were those people who provided good models, good pictures, good algebraic structures for dealing with this geometry. So here is a rough timeline of what happened. So Around somehow 300 BC, Euclid's Elements were written, and perhaps the only book you can compare Euclid's Elements to in terms of having reprinted issues of the book is the Bible. And so in a sense, Euclid's Elements are the second most important book, and mathematicians like to consider it like that. Around 900 in our time, people started to question, is the parallel postulate really independent? And so this remained a puzzling question with many attempts and many failing attempts until, well, essentially these three people here entered the stage. And one can say between something like 1813 and 1832, these three people independently discovered that there is something like a non-Euclidean, in this means hyperbolic geometry, because you can prove hyperbolic geometry is up to isomorphism the only geometry that satisfies the first axioms but not the fifth one. And the story behind this discovery is really a very personal one. And also the story about the many attempts is an exciting one, but this would really go beyond the scope of that lecture here. And a few years later, Beltrami and Klein gave interpretations in terms of what we would today call Cayley Klein geometries, and even a few years later, Henri Poincaré gave another nice model in terms of what today is called the Poincaré disk model. We will meet all these things later, but let me first come to this benchmark point in mathematical history, and let's talk a little bit about the relation of Gauss to the Bolyais. And here I have taken a plural S here because you have this János Bolyai, and this János Bolyai is the son of Farkas Bolyai. Both of them lived in Hungary, and well, one was father, one was son, and both of them worked on non-Euclidean geometry. So the father was actually a friend of Gauss, so they know each other from their early days, and perhaps he got inspired by Gauss to think about non-Euclidean geometry, and he always wanted to prove the dependence or independence of the fifth postulate, and he really failed in that attempt, and the young son finally resolved this problem. Important side remark, if you do important work on hyperbolic geometry, you end up at a stamp, so you can find all the important people discovering non-Euclidean geometry and working on it in some stamps in some countries. So as I said, Farkas Bolyai failed in some way, and there is a really great letter from him to his son where he wants his son not to work on hyperbolic geometry, and he wrote that letter in 1820, and I want to read from that letter, and I do that in German because I don't have a good translation to English of that letter. You can find a rough translation of it in the Perspectives book. So let me read from that letter. Du darfst die Parallelen auf jenem Weg nicht versuchen. Ich kenne diesen Weg bis an sein Ende. Auch ich habe diese bodenlose Nacht durchmessen. Jedes Licht, jede Freude meines Lebens sind in ihr ausgelöscht worden. Ich beschwöre dich bei Gott, lass die Lehre von den Parallelen in Frieden. Du sollst davor denselben Abscheu haben wie vor einem liederlichen Umgang. Sie kann dich um all deine Muße und die Gesundheit, um deine Ruhe und dein ganzes Lebensglück bringen. Diese grundlose Finsternis würde vielleicht 1000 Newtonsche Riesentürme verschlingen. Es wird nie auf Erden hell werden, und das armselige Menschengeschlecht wird nie etwas vollkommen Reines haben, selbst die Geometrie nicht. Es ist in meiner Seele eine tiefe und ewige Wunde. And so on and so on. So you see, this is just a brief excerpt of that letter. He was really emotional about that, and he warned his son, but despite all warnings, the son really can be considered as one of the independent discoverers. And since Farkas Bolyai was a friend to Gauss, he wrote about the discoveries of his son to Gauss, and here you see the stamp of Gauss, and he wrote back, and this really was, I would say, challenging their friendship, the following letter, and this happened in 1832. Jetzt über die Arbeiten deines Sohnes. Wenn ich anfange, dass ich solche nicht loben darf, so wirst du wohl einen Augenblick stutzen. Aber ich kann sie nicht anders. Sie zu loben, hieße mich selbst zu loben. Denn der ganze Inhalt der Schrift, der Weg, den dein Sohn eingeschlagen hat und die Resultate, zu denen er geführt ist, kommen fast durchgehend in meinen eigenen, zum Teil schon seit 20 bis 25 Jahren angestellten Meditationen überein. That must have been a shock for Farkas Bolyai, because Gauss never told him that he knows everything, what to do, and he had to go Farkas Bolyai, and he let Farkas Bolyai essentially go through the hell of the finding non-Euclidean geometries. And it's pretty sure that Gauss already, if you look at these 20 to 25 years here, knew everything about non-Euclidean geometry quite a while ago. And then there is another person, Nikolai Ivanovich Lobachevsky, who also can be considered to be an independent discoverer. And at some point, the Bolyais actually suspected that Lobachevsky is a pseudonym under which Gauss wants to publish his own results on non-Euclidean geometry. But, well, it is not. Lobachevsky really was a living person with his own stamp. So let me look at what Gauss actually knew and at least explain a little bit why he never published anything on that topics. So the first ideas where we have written certificate that Gauss knew about it goes back to 1813, but after his own claims, it must go back to 1807 or so. NEG here means non-Euclidean geometry. So he started to think about these things really early. And one reason why he didn't publish anything about that was that he didn't want to get in conflict with the leading philosophers of his time, namely Kant's school. If you know Kant's Kritik der reinen Vernunft, one of the first statements there is that there is some kind of a priori knowledge, things you know without even ever measuring it. And among those things, he considered the nature of a straight line to be knowledge a priori. And well, what Gauss did with his investigations of non-Euclidean geometry, he essentially proved that it is not that clear what is the nature of a line, and this would be a major conflict with the main philosophers. He most probably had a pretty complete theory of non-Euclidean geometry. So you must know, at that time, Gauss was among the most famous mathematicians of his time. And whenever people worked on that problem, they sent him letters and asked him, Mr. Gauss, can you tell me, is my proof of the fifth postulate, is this correct? And Gauss almost immediately was able to turn down each of that false proofs because he knew at what point he had to look to really point out the error in such proofs. There is an interesting thing. So Gauss was a geometer, and a geometer really in the literal sense, meaning geometer. So he measured the earth, and he had a position in which his main duty was to measure the earth and to really find good methods for cartography and for measuring distances and measuring angles. And it seems to be very likely, if you look at some of Gauss' notes, that among these works as a geometer, he tried to measure really big triangles. So if you look in the literature, there are several sources that claim that Gauss, in his profession as geometer, went to three mountains: the Hoher Hagen close to Göttingen, the Brocken and the Inselberg, which are pretty high with respect to German standards and pretty far apart, so you get a really big triangle between them. And he wanted to measure whether there was a deviation of the angle sum of that big triangle to the 180 degrees that you would get in Euclidean geometry. As you can imagine, up to the measurement exactness, up to the error bound, he was not able to detect kind of deviation from Euclidean geometry. I have to mention there's at least one paper that doubts that Gauss really did that, quoting several sources and digging into the history of it. But there's also another paper that doubts the doubts of this first paper. So I would say it's really undecided whether Gauss really did that or not, but at least it's a great urban legend somehow to say, well, Gauss went to these hills and measured these big triangles. And until his death, he never published anything on non-Euclidean geometry, so we only know about Gauss' investigations of non-Euclidean geometry from letters he wrote to other persons that only became public after Gauss' death. Let me briefly mention a few numbers or a few dates here. So, as I said, Gauss perhaps did first works on that already in 1807. He definitely worked on it in 1813, and in 1820 he definitely knew a lot about it. We know that from his letters. If we look at the other two, Lobachevsky and Bolyai, they were much later. And if you look at living dates here, all these three people here lived approximately to the same year. So Bolyai's son lived perhaps the longest of all of them until 1860. But both Lobachevsky and Gauss only did get recognition of their work after Gauss' death, because Gauss was the only person who people trusted mathematically at that time, and so these here were considered as kind of esoteric thoughts. But since the big Gauss also had the same thoughts, those two persons after 1855 got some recognition for their work. By the way, János Bolyai published his work on non-Euclidean geometry as an appendix of a math book of his father. So it deserved really, it should have deserved a more prominent place, I would say. So let me conclude our history lecture with a little pointer to Beltrami, Klein and Poincaré. We will go into details there a little bit later. So the Beltrami-Klein model is exactly what we learned in the context of Cayley Klein geometry. So it's embedding the hyperbolic plane as the interior of a non-degenerate real conic in the Cayley Klein geometry, and we get those lines which are really lines, and we get those different parallels to that line, things I told you. This is really important work in that context, because what all the other people, Gauss, Bolyai, Lobachevsky, did was developing a theory of something that is non-Euclidean, but they didn't have a model of that in terms of Euclidean geometry. And what we have here is a picture that tells us if you believe in Euclidean geometry, then you also have to believe in projective geometry, then you also have to believe in Cayley Klein geometries, then you also have to believe in hyperbolic geometry. So if one of them is free of contradictions, then also the other has to be free of contradictions, which is from a logical point a really big step forward done by Beltrami and Klein. Then a few years later came Poincaré and offered another model of the hyperbolic plane. It also is embedded in the interior of a circle, but this time this circle is considered to be a circle in CP1, in the complex projective line, and this time the lines are not straight in that model. They are circular arcs that are perpendicular to the boundary of the limit circle, and it turns out that this model here, although the lines are no longer straight, has many advantages with respect to the Beltrami-Klein model, and we learn about those advantages in our next lecture. Just let me give you one picture. I told you that in the hyperbolic plane you have such beasts like all right angle pentagons. And what I've drawn in that picture here is a tessellation of the entire hyperbolic plane with all right pentagons. So any angle that you see here between lines is indeed a right angle with respect to the corresponding measurement. So you get a kind of pavement of the hyperbolic plane with right pentagons. And if you draw the corresponding picture in the Poincaré model, you see it looks much nicer and much more harmonic. So the lines are no longer straight, they are circular arcs. But if you look at it, the angles here really look like right angles, and this is one of the big advantages of this model, that angles really can be considered as Euclidean angles in that measure. So a right angle really looks like a Euclidean right angle. This is one of the advantages, and the other advantage is that it has much more space at the boundary. So you see much more structure in the Poincaré model than you see here, because it sacrifices space in the interior, where nothing happens essentially, for space at the boundary. In our next lectures, we will learn more about Poincaré model and its relation to the Beltrami-Klein model, and we will see how multiple the advantages of this model are compared to Beltrami-Klein. I will see you there.